let's consider the case of heat transfer through multiple layers of a slab. So we've got a 3-layer slab here, and I've numbered each of the interfaces 1, 2, 3, and 4. And we'll assume that we have heat flowing in on one end and heat coming out on the other. In this analysis, we're going to consider that the sides of the slab are insulated so that heat is only flowing in the direction shown, unidirectional, right? Okay, so if the sides are insulated, we can assume that all the heat that flows in will also flow out at steady state. And so that means that the heat flowing into layer A is the same as that into B and the same as C, so on and so forth. So now, given that, we can also rewrite Fourier's law to emphasize the temperature difference. So for this first layer, A, we have that the temperature difference between T2 and T1 is equal to the heat flow, the thickness of the layer, divided by the area of that layer, and the thermal conductivity of that layer. So we can do the analogous form for B, an analogous form for C, and then let's add them all up. And if we do that, we see that because all of the Q's are equal, we can take that out of parentheses, and then we just have this expression which is effectively the sum of thermal resistances. And on the temperature side of the equation, all of the intermediate layer temperatures cancel out, and we're just left with the temperature difference between the top of the slab and the bottom of the stack. And that's actually the quantity we're interested in. If we can avoid calculating every intermediate temperature, that probably saves us time. Okay, so this is a quite useful result. We'll highlight it here. Next, we need to apply some definitions to simplify it. So we're going to define the thermal resistance as this quantity, delta X over A over thermal conductivity for a given layer in the slab. And I'm putting an overbar on the R to indicate that this definition contains the area. So coming back to our definition of Q, we can basically see that Q is just given by the overall delta T across the stack divided by the sum of thermal resistances. So that's a very handy definition for solving any kind of multi-layer problem. Again, that overbar in the resistance means that the area is included in the resistance terms. That's important to note because sometimes the area is constant, like in the schematic I'm showing here. And so when the area is constant, you can actually multiply both the top and the bottom of the equation by the area. And when you multiply the sum of thermal resistances by the area, it cancels with each of the terms in the thermal resistance. And so it's another way of expressing the equation, and we would often do it like that when we don't actually know what that area is. So it's a nuance, but if there's no overbar in the expression, then that means the area has not been included in the thermal resistance, so you should look and make sure that the area appears somewhere in your multi-slab Fourier law expression. Okay, the final twist on this we're going to do is to define thermal conductance, or sometimes called the overall heat transfer coefficient. And that is just the inverse of the sum of thermal resistances. And if we reflect back on the Fourier law that we just defined, we can easily see that this leads to the expression Q is given by the overall heat transfer coefficient times delta T. Again, the U has an overbar, and so that means that area has been included in the definition of thermal resistance. But if we were not to include area in that definition, then the area would effectively pop out and you'd have to include an area in your Fourier's law definition. So these are the two really easy expressions to use. You can pitch it as overall heat transfer coefficient or thermal resistance. Both are equivalent. The one main caveat you have to bear in mind is that this mathematical formulation only works for slab geometry. And that's because the area actually is constant with each layer. So we'll see that when we get into cylinders and spheres, the expression for multi-layers becomes a bit different. In the meantime, let's get on and apply this to example 3 in the notes.